right. Thanks, everybody. All right, so we are going to start this tour by explaining a little bit of background information about our ship and about the science that we're doing. And then we will take you to see how we run our ship, how we drill into the ocean floor. You'll get to see some of our labs, and you'll get to hear about the science that we're doing. So it'll be a lot of me flipping back and forth with the camera, so please be patient with me. All right, so this is an image of the JOIDES Resolution. It is an ocean drilling research ship, which is what makes it a very special ship. And you can see that unlike most other ships, sorry, we are in a hallway, so we have to share the space. Unlike most ships, this one has what we call a drilling derrick. And usually when we think of drilling ships, these are ships that drill into the ocean floor for oil and natural gas. But we drill into the ocean floor to collect rock samples, these cores of rock, and we use it entirely for scientific research. So there is no profit to what we're doing. We are really here to just learn about the Earth. And the JOIDES Resolution is operated by an organization called the International Ocean Discovery Program. And I am going to show you a map of the world. And what you can see is that in all of the oceans, there are these dots. And each dot represents a location that the JOIDES Resolution, or one of our previous drilling ships, has drilled into the ocean floor. So we've been operating for about 70 or 80 years now, and we're getting to the point where there are very few places where we have not been to learn about the oceans. So the JOIDES Resolution has been really integral to understanding plate tectonics. Some expeditions learn about climate change and climates in Earth's past. Something else we've been focusing on a lot recently is the origins of life and the extreme environments in which life can live. But I'll explain our expedition, which is a little bit different and a little bit special, but first some more geographic background. So this is where you all are approximately in India. And Rajneesh, how long did it take you to fly to Cape Town?
Oh, it was 14 hours flight time.
Wow.
With a layover of 2 hours.
Okay.
Yes.
Mm-hmm. So where was your layover?
While coming, it was in Addis Ababa.
Okay.
In Ethiopia.
Uh-huh. So, okay. So you flew where Ethiopia is around here?
Yeah.
And then down to Cape Town, South Africa. So 14 hours of flight to get here from where you live. I am from New York City in the USA. So I flew from here all the way down to Cape Town, and that was also 15 hours of flight time, so a very long flight. But what we did in Cape Town, we both spent 4 days, each in our own hotel rooms for isolation. And after that, we boarded the ship, and we sailed from the ship to this feature over here on the ocean floor called the Walvis Ridge. So to zoom into what that looks like in a little bit more detail, this is the Walvis Ridge. And you can see that there are some notable features about this ocean floor feature. So to the northeast, we have what's called the Valdivia Bank, and it consists of this really broad plateau that kind of changes direction. And then toward the southwest, it branches into these 3 distinct chains of seamounts. So scientists have figured out that the Walvis Ridge is what's called a hotspot. So I'm sure as geologists, you all know what hotspots are, but just in case there's anyone who doesn't remember or is unfamiliar, I'll explain that in a little bit more detail. So Earth is composed of layers. We all live on the crust, and below the crust is the mantle. And different regions of the mantle have different heats, different temperatures, and also different densities and different buoyancies. So sometimes there are locations in the mantle that tend to be much more hot and therefore more buoyant. So they rise towards Earth's crust. And since they're so hot, they're actually able to melt the overlying crust, and that forms a volcano. due to the motion of plate tectonics, over time, that volcano will get moved away from the hotspot, the mantle plume. And so the old volcano will move out of the way and a new volcano will form in its place. And what that results in typically is a chain of volcanoes that get older and smaller as you get farther from the mantle plume. A really classic example of this are the islands and seamounts of Hawaii in the Pacific Ocean. And so again, what you see is this really straight line, first of volcanic islands, but as they get older, they've experienced more erosion, so they get smaller and smaller, and eventually it becomes a chain of seamounts. Another example of that is the chain of Louisville seamounts in the Southern Pacific. And again, what really stands out about these hotspot tracks typically is that they form a straight line. So we know that the Walvis Ridge was also formed by a mantle plume, but when we compare its morphology to the more typical hotspot tracks, we see that it is very, very different. Instead of a straight line, we have a squiggle over here, it zigzags. And instead of one line down here, we actually have three. So what we are doing is drilling into the ocean floor at the Walvis Ridge to collect rock samples that will hopefully help us answer the question of what exactly is going on in Earth's mantle that's causing the Walvis Ridge to look so unusual compared to other hotspots. So I will face the camera to me just to give a little bit more background about the expedition. So this is actually the second time this year that the JOIDES Resolution has been to the Walvis Ridge. We initially sailed here on expedition 391, which was from December to February of this year. But unfortunately, in the first week of the expedition, several people tested positive for COVID-19, which meant that we had to delay our expedition by about 2 weeks. So the original plan had been to drill 4 or 6 different sites, 3 up here in the Valdivia Bank, and then 1 in each of these distinct chains of seamounts. But unfortunately, since we had to cut our time short, we were only able to drill 4 holes. So Expedition 397T, which is currently taking place, the goal of this expedition is really to transit the JOIDES Resolution from Cape Town up to Lisbon in Portugal, because the next several expeditions are going to take place in the Mediterranean Sea. But as you can see, that transit crosses directly over the Walvis Ridge. So we were lucky enough to have some extra time to take 2 weeks to drill those 2 additional sites that we didn't get to the first time. So that is what we're doing here. And now what we're going to do is see a little bit of the ship and then go into the labs so we can hear more about the science that Rajneesh and all of the other scientists are doing. So on ships, we have what's called watertight doors, which the name should speak for itself. We need to make sure that if there are ever big waves, we never have to worry about the water coming onto the ship. But it means that they're very heavy and they're hard to open and close. So I'm glad that Rajneesh was able to get that for me. All right, so everybody, welcome outside. This is our view, starting to have some cloudy weather. Right here in front of me is one of our lifeboats. So we have 4 of these on the ship, and each of them holds 70 people. So we can rescue a total of 280 people, but luckily we only have about 130 people on the ship. And also we've never had an emergency, so we've never had to use them. But just in case, something that we do is every week we have evacuation drills. So the captain will sound the alarm on the ship, and we'll all put on our hard hats and our safety glasses and our life vests and practice going to our assigned lifeboats just in case of an emergency. We're going to walk now towards the front of the ship. And so these windows that you can see in front of me, these are part of what we call the bridge. That is where the captain works. So it might get a little bit windy. All right. So welcome to the front of the ship. Obviously, the captain is responsible for steering the boat, so he needs the biggest window so he can see where we're going. But honestly, a lot of what he does is based on GPS systems. So a lot of our steering is actually automated, but it's still really important that he can see the ocean just in case of anything. Another thing that you can see in this part of the ship is this big gray cylinder. This is called a thruster, and it is part of our dynamic positioning system. So when we drill into the ocean floor, usually it's much too deep for us to use an anchor to hold us in place. And even if we used an anchor, it wouldn't be enough to keep us from moving. So there are 6 of these thrusters that have propellers at the bottom of them. So when we get to our drilling site, they will all go down into the ocean. And again, using GPS, they will keep the ship in place for drilling. Something else that you can see is our picnic tables. One of our lab officers is reading a book and drinking his morning coffee. So something about life at sea, maybe Rajneesh can add on to this. Because this ship is so complex and so expensive to run, it's really important that we operate at all times of day. So everybody on the ship works a 12-hour shift, and most people work either from noon to midnight or midnight to noon. And that way there are always people working so that we can operate 24 hours a day. So we each work 12 hours a day, 7 days a week. Typical expeditions are 60 days long. So we work very, very hard. But on the other hand, they make it possible for us to be very comfortable during our off shift time. So one of those examples is that we have these picnic tables where we're able to sit and enjoy ourselves when we're not at work. It's also a really lovely place to eat our meals. Do you have anything to add?
No, I just wanted to add to this that because everybody is working for 12 hours and they need some kind of recreation. So the ship has not only picnic table, it has a full gymnasium, very well-equipped gymnasium. It also has a music room, a lounge with enormous amount of books. You have books of all genre, all types of books are there for a reading room. So all kinds of things are taken care on this ship. It is very interesting to see all these things.
And another thing is that all of our meals are cooked for us. So at 12 noon, at 6 p.m., at midnight, and at 6 a.m., our kitchen offers a full meal. So we don't have to cook for ourselves, we don't have to clean for ourselves. So we work very hard to do our science, and in return, we're taken care of. So now we are going to walk around the front of the ship, and that will bring us to see the back of the ship where all of our drilling operations take place. Oh, hi. Sorry, excuse us. All right. One thing that you can see here is one of our cranes. So we have 3 cranes on the ship, and they are really important for many of our operations because we have to, for example, we have about 130 people on the ship for every expedition for 60 days, which means we need to get that much food and toilet paper and soap and cleaning supplies onto the ship. The crane also helps us move our drilling pipes around. And behind the crane that we're going to see very soon, it makes our ship so special compared to other ships. So this structure here is what is called the drilling derrick. It is about 62 meters tall. And this is the structure that supports all of our ocean drilling. So before we get closer, I'll just point out some of our drilling pipes, which you can see stowed down here. Each of them is about 10 meters long. And the way that we operate is we attach pipe after pipe after pipe to each other. And that's how we get from the ship down to the ocean floor. So typically where we're drilling, the ocean floor can be several kilometers deep. So we have to get, I think at the locations where we were drilling this expedition, the water was about 2.5 kilometers deep. So we get down to the 2.5 kilometer deep ocean floor, 10 meters at a time. So it ends up taking 8 to 12 hours to connect that many pipes to reach the ocean floor before we can even start drilling. Another thing that you can see here is this big line of yellow and black tape. That means that where we're going is a hard hat and safety glasses area of the ship. So sorry, the phone's falling. Yep, I'm gonna put on my safety glasses so that we can follow the ship's rules. Thank you. All right. So this is an area of the ship called the rig floor. We have finished with all of our drilling operations. So that's why you do not see anything going on anymore, unfortunately. But that white rectangle is covering up the part of the ship that the drill would go down into. So we like to make the joke here. It's not often that you'll find a ship that has a hole in it on purpose, but this part of the ship right here is the whole reason that we're here. And so what you can see, this is the engine that spins the drill. This is what we call the top drive. It's the engine that powers the drill. And the way that it works is this yellow structure can go all the way up to the top of the derrick. And that supports what we call the drill string, all of those pipes connected to each other. And it's really complicated to drill from a ship because maybe you can even see right now, the ship is moving. It's constantly moving up and down because of the waves. So this structure has what's called a heave compensator. It's essentially on a set of giant shocks. So we can compensate for about 8 meters of up and down movement. But if the seas are more active than that, if the waves are bigger, we actually have to stop drilling because the motion of the ship could actually damage the drill pipe. We're going to now go down a set of stairs to see where the actual analysis of science begins to happen. So this is a part of the ship called the catwalk. Before we talk about the science that happens here, I just want to show you how we drill into the ocean floor. So this expedition, we have been using what's called a rotary core barrel drill bit. And so what it has, it's sitting upside down when it's in use, the spiky parts would be touching the ocean floor. And so the drill spins this drill bit, and each of these 4 roller cones rotate, and these nubs are made out of a material called tungsten carbide. So they're very, very, very hard. And so as they rotate, they grind away at the rock on the ocean floor. And in the center, you can see that there's this hole. This is where a tube of rock gets preserved. We call it a core. And those are the rocks that we collect. So this is what's coming out of the rig floor every time we drill. We end up with a core of rock that's 10 meters long. So it'll come out of the drill, they'll turn it horizontal and place it on that yellow stand right there. And then our drillers will pass it to our technicians who carry it from the rig floor to the catwalk. So I actually missed all of the coring operations during this expedition because I caught COVID, but Rajneesh was here. So do you want to talk a little bit about the experience of being on the catwalk?
Yeah, it is always exciting to see what is coming out of the depth of the sea floor. So everybody you find standing here and excitingly and eagerly looking forward to what comes out of the core this time. And here I would like to add one more point what Maya was telling, that this RCP, the rotary core fitting rigs, they are very, very appropriate for the hard rock drilling. So here this expedition was aiming to collect the core of the basement. So that is why this RCP was chosen. This JR also drills for the soft rock, for the sediments. And that time they use, I think, piston core rigs. So there are two types of drillings which this JR does. One is for the sediments, which is used by the piston core, because in this rotary core, the bits rotates and all the things are rotated, so sediments get disturbed. So sediment recovery is not very good. But I was amazed to see that even the sediments were recovered very good in some of the core sections. So this drill core is, I think, is a very advanced thing to even recover some of the sediments, as well as excellent recovery of the hard rock. In fact, it was so excellent it exceeded 100% in some of the sections.
Yes. So when we go inside, we'll get to see some of those cores that were collected. But again, when the core comes out of the drill, it's in what's called a core liner, which you can see an example of this clear plastic tube. So when it comes out, again, it's 10 meters long. So that takes up the space of all of these tables. But as you can imagine, 10 meters of rock is very long, it's hard to work with, and it's also very heavy. So what our technicians do is they cut it into sections that are about 1.5 meters long that look like this. So again, this example is empty. It's just an example. When we go inside, we will see what it looks like when it has core inside of it. But each of these core sections is what we will begin to work with to analyze the rocks. So now we're going to go inside our core lab. Thank you. All right, so this is where we begin our scientific analyses. And again, since we've finished all of the core collection, you don't see a lot in this section of the lab. But when we get to the other section, you'll get to actually see some core samples and learn more about the geology. But the first thing that happens when cores come out of the ground is they get placed on these shelves. You can see an example of that over here also. And what needs to happen is that the cores need to get brought to room temperature. And that is because the first analyses that we do are based on knowing the physical properties of the rocks inside the core liner. So we need to make sure that it's not affected by temperature changes. And something else you'll notice is you can see that these tables are made very specifically to hold those tubes of rock. So everything that we have in our labs has been designed specifically to work with cores collected from ocean drilling. So in addition to scientists, we have technicians, we have engineers, we have electricians, we have welders who all work together to create this lab space that we can use to study our rocks. So here is an example of what it would look like to see a core full of actual rock. This seems to be some sediment collected from the ocean floor. And so some of the physical properties that we record are density, thermal conductivity, magnetic susceptibility. Can you think of any other ones? Reflectance, yes. And so all of those can be done while the core is still inside the core liner. But then what happens, because we want to be able to access the rock that we've collected, we take them into this room, which we call our splitting room, which it doesn't seem like anyone's in there right now, so we can go in. And this is a giant track that we use to split our cores in half. So it's a track that will slide the core on, and the saw will come down the length of the core to cut it in half. And that allows us to access the rocks inside so that we can study them. So I'll show you where we store our cores. You can see that this section of them, these are all of the section halves that we've collected this expedition. These are the ones that have black caps on them with a W. That W stands for working half. So these are the core samples that scientists are actually able to touch, interact with, collect samples from. And these are the halves of the core that get used for the scientific analyses that we do. The other half is what's called the archive half, and you can see them over there with the red labels. And the archive halves are not touched by scientists. So what happens with those is that they are sent to what's called a core repository, where they are stored. And that is the undisturbed record of every core that we have ever collected. When Rajneesh talked about the excitement of being on the catwalk and waiting for cores, something in addition to that is that when we're on the ship, we are the only human beings on the planet that have access to these rocks. It takes so much time and so much effort and so much money to be able to drill into the ocean floor that what we collect is really, really special and really, really unique. So that's why, in addition to using half of the cores for scientific analyses, we keep half of the cores undisturbed just for that geologic record. And there are 3 core repositories in the world. There's one in Texas in the United States. There's one in Bremen, Germany, and there is one in Kochi, Japan. So now that we are in the core lab, I will turn it over to Rajneesh and some other scientists that we'll meet to talk a little bit more about the science that we do.
Well, this course here, which we see, is from the last side, and every hole is given a unique number. So you can see here, this hole is U1584. And U stands for United States, so that is what it is, right?
I didn't know that. Okay. I believe it. I just learned.
No, whatever is drilled by the JR, they are given the number U, so it is 1584. A is this first hole. If you have this another hole in the same site, then you will give the number B. So this is a unique number, and this number is continuing from last 60, 70 years, I believe, even though the program's name have changed. Earlier it used to be called DSP, Deep Sealing Project, Deep Sea Project, and then ODP, Ocean Drilling Project, and then IODP. So 2 IODPs I read. Yeah.
Yes,
second IODP.
The Integrated Ocean Drilling Program,
yeah.
And now it's the International Ocean Discovery Program.
So the course here are the first course. This is the core number 3. So this is the first core which came out of the first site that was given the name 1584. And what you see here is basically sediments. And the interesting part of the sediments is that you can see a lot of bioturbation in this. You see all these are the bioturbation marks that you see here. And as I told you that these drilling bits are designed basically for the hard rock, but even then you have good discovery. But in that case, you see some of these drilling disturbances. You see this is called the biscuiting, where sediments have moved in the fracture caused by the drilling. So these are some drilling disturbances. And these are the sediments which are essentially used by the biostratigraphers. They will take out the nanofossils and foraminifera from these, and they will give us the exact date when the sediments are actually deposited. Unfortunately, right now we do not have biostratigrapher with us, but the samples would be sent to them, and you see all these flags are the flags where the samples would be taken and sent to these biostratigraphers who would take out the foraminifera and nanofossils and give us the precise age when the sediments were deposited. So all the sediments were deposited on a volcanic or on a sea mount. And once we go deeper, then we start seeing the effect of those volcanoes. So these are what we call lapilli stones, which are basically volcaniclastic sediments. So we have classified them as a sedimentary core again, because they are not the in situ volcanic products. They have been settled and redeposited, but they've all come out of the volcano. So all these tiny things which we see, the yellow, if you can see it, these are all very vesicular pieces of the ejecta. So it can be called a scoria or a pumice, because when you see it closely, you will see large number of vesicles in this. Some of them are filled with the secondary minerals, some of them are not filled, and they have also caught up some basaltic clasts. So you have not many such basaltic volcanic clasts which have been caught up by this ejecta. So these are all volcanic clastic material which was down those sediments. So these are the deeper cores. They are the core number 7 and further. And what you would see interesting cyclicity in the color. You can see this is yellow, and then it is going towards much coarser size. You see much coarser class there. And again, it will go to the finer particles, and again, it will go to the orangish coarser. And this continues, but the color changes there in those deeper cores, which are much more rich. So this color change is basically due to the alteration, and this brownish orangish to this greenish alteration. Basically, all this material is same. We call them lapilli stone, but the color change is due to alteration, and this is because those were more oxidizing fluids which were altering the rocks. These are more reducing fluids which have altered these rocks. So one of my project is to study this alteration. So these are quite interesting from that point of view. But the major objective of this expedition, as Maya had explained in the beginning, to understand the plume-related magmatism, the hotspot-related magmatism, and why this Valvis-rich hotspot is so different from the other hotspots geochemically, as well as even plate tectonic-wise. People are debating that the plume migrated, or it was an actual migration of the paleopole. So all these questions will be answered when we get the massive flow basalts. So for that reason, we moved to the second site, and we got the many massive flows, very huge, massive basaltic flows that came out from the second site, which were very interesting. But right now, those are not on the table.
So I'll flip the camera so that you can keep talking, and I'll go grab a basalt core.
Okay. So in the meantime, and Maya actually brings the actual massive flow basalt, what I would like to do is to show you some of the cores from the second site. They were all about the massive basalt, but they were also sediments. But they are very interesting sediments, and luckily they are on this table where our very senior colleague, Professor Mike Widdowson from UK is working on. So let me see how to flip back the camera, and I'll just like to ask him to.
Oops.
Okay, thank you.
Yeah.
So Professor Mike Widdowson is from UK, and he's very well-renowned volcanologist, sedimentologist. He has worked extensively in India as well. I think he has lot many papers on Deccan traps. So, I would request him to explain these particular. I will actually, in general, he can explain lot many things, and he's right now looking at these interesting sediments which came out from the second site on top of those massive basalts, and you can see the cyclicity in this also, but different color cyclicity. And some people believe that they are climate control sediments. So I would now request Professor Mike Widdowson to please speak to our students. And
yeah. Hello, everybody. It's a real pleasure to be here on the ship and working with your Professor Rajneesh Patani, whom I have known. He's worked for many, many years. He's correct. Normally, I work on flood basalts, which the Deccan is a very famous example, but I've changed roles slightly here, and I am looking at both the sediments and the volcanology succession on top of it. So I'm trying to get the whole story, put the history of what's happened at this part of the ocean, not only in the depths of the ocean, but what has been introduced through volcanic input, which you've seen in the previous cores. So the succession I'm looking at here is deep sea silts and clays with quite a lot of biogenic input in terms of micro and nanofossils. You may be able to see there are lots of little patterns in this, which is where organisms are burrowed in. So there's an awful lot of bioactivation. And Rajneesh has also pointed out to you the variation in color, which goes from reds through to greys, and this is quite regular, and we've seen this elsewhere in other cores from other sites on the Walvis Ridge. And we believe this is something to do with climate over a long period of time. It may be related to orbital variations of the Earth, and it may be related to productivity as well. That has yet to be analysed when we go back to the labs, and other scientists will work on that and try and extract that signal information. The other thing that we can see in this particular succession is evidence for deep marine slumping. So, for example, you may see at the top of here, there are a series of fractures running through the sediment, which tells us there was a brittle failure here. And then on top of it, we see this quite complex series of lozenges of sediment, which is stacked one on top of the other. This is quite chaotic. And what we think is that there's been a submarine landslide, which has brought these soft, broken up ripple clasts and redeposited them on the seabed. And as he's done so, it's loaded the seabed and fractured the seabed to create a pile of introduced material. So it's a kind of landslide and turbidite which is going on, which is exactly what we'd expect in and around volcanic islands, where eruptions are going off and the ground is shaking and destabilizing material which is stored in the shallow water and then allowing it to cascade into the deeper water, producing these kind of sediments. So it really is part of our responsibility, because as Maya was saying, we're the very first scientists to see this. It's our responsibility to make as good a record of the detail of these cores in order to fulfill the scientific objectives. So that's really my task for today, is looking at the detail, literally centimetre by centimetre, and trying to tell the kind of story that I've just outlined to you. So I'll pass back to Rajneesh and Maya, and it's been a real pleasure talking to you.
Thanks, Mike. All right, so I took out that basalt. If you want to talk a little bit about the basalt.
Yeah, so you can see this massive, this is part of the massive flow, and this is a very deep core, so you don't see much vesicles in this. But on the top part, we could see a lot of vesicles. What you see here is a gray color, a typical basalt looking color, which has, when we have now thin sections also to examine, so we know that there are good olivines, good pyroxenes, and plagioclase, which actually, and which make very interesting texture in this particular type of massive flow, which is not very common to the other type of basalt that I have seen. This is the framework of basalt which actually holds up, and you have in part some mesostasis, which is basically the crystals which could not be completely crystallized. So we see a lot of mesostasis texture, and we see the framework of the feldspar which holds up the entire rock. It is interesting to see the thin section of this. And from my own personal interest, I would see that a lot of alteration which was not seen on this megascopic scale is visible on microscopic scale. So we see a lot of chloride formation. The feldspars have been sericitized. So they all tell us a story, a coherent story, which goes along with the volcanism and in secondary alteration. So here you can see one of the structure, which is filled by the two minerals. In fact, you can, I don't know whether you can appreciate this, but there is a white color and there is a slight greenish color. So these two are the secondary and two phases of secondary alteration which has taken place in this massive basalt. But our isotope geochemists, our paleomagnetists who are working on this core for the primary objective expedition, they are very confident that they would be able to solve the mystery of this Walvis Ridge. That how come you have two different isotopic signatures on the same plume? That is one problem which we are addressing, and how come you have different paleomagnetic cores from this Walvis Ridge basalt. So this is one example of that massive flow. This is what I was talking about on the catwalk also, that in some core section, we got more than 100% of the core. So that was excellent recovery that you can have from these volcanic islands.
So the last person that we will talk to in our lab, Rajneesh talked about paleomagnetism as one of the things that we do. So over here, we are coming to see Dr. Claire Carvalho. who is one of our paleomagnetists.
Recording mode.
So what are you doing?
Right. So,
It came as a recording mode and all. Just
measure the magnetization of the rocks, and especially the direction of the fields that they have recorded when they were formed. So either the sediments when the little magnetic particles fell down and were deposited, and then they oriented in the direction of the field, or in volcanic rocks when the rocks erupt. The little magnetic particles can also orient in the direction of the field, and then when the rocks cool down, then this direction is frozen. So when we take these rocks now, we can measure the direction of the field that they have recorded when they were formed millions of years ago. So the important things, because we're looking at directions, is the orientation. So these are the samples that I am studying, measuring. So they have this is the direction down the hole like this, and this is really very important to know. So I have some samples that I demagnetize using alternating field demagnetization. So I apply alternating fields higher and higher, stronger and stronger. And then some other rocks, they are in the oven, which is here. And I heat them at temperatures in temperature steps higher and higher, and it's the same idea. I will erase the magnetization in temperature steps, and then they will give me the better estimate of the direction of the field that they have recorded. Okay.
Thank you, Claire. All right, so this is the tour of the core lab. In addition to this floor, we have another floor where we have a geochemistry lab, we have an ICP lab and an XRF lab. We also have a lab where we make our own fin sections. But in the interest of time, I think you're all on your lunch break maybe. We want to make sure that you have plenty of time for questions. So we're going to come over to my other computer, and if you have any questions, we're happy to answer them. So I'm going to turn off this camera here and connect on my computer, and then it'll be a lot easier for us to see all of you and answer your questions. All right, so we are now at the computer. If you have any questions for me or Rajneesh, please feel free to answer them.
Student, you can unmute and ask, please.
You can also type in the chat if you feel more comfortable with that.
I have a few questions. Can you hear me?
Yes, go for it.
So what makes these sediments to be loose when we are drilling it? I mean, these loose sediments are intact actually, but they should be very loose. Like when we are drilling it, they should be fragmented, right?
Yeah, actually in this expedition, they did not start taking the core of the loose sediments. In fact, they started coring only just 20 meters above the basement. What it means is that most of the loose sediments were actually washed away. And that was intentionally done because we did not have time to actually take out the loose sediments out. So it was decided before the expedition, and for that, they have to take a permission from the Environmental Monitoring Agency. I think it is called ESP.
The Environmental Protections Agency, maybe?
Yeah, so they give us permission to wash down those loose sediments without collecting the core. So it was pre-planned. So core started they started collecting the core just 20 meters above the basement. So it is mostly lithified sediment that we collect.
And part of the drilling process is to pump fluid down into the drill. This is the process that causes the drill to spin. So sometimes if the sediments are particularly unconsolidated, the drilling fluid will just wash them out of the core. You want to sit down?
No. Yeah, and one more thing, like at what depth I mean, what is the maximum depth of drilling which has been carried out in the ocean floor?
So the ship has the capacity to drill 8 kilometers of depth, whatever combination of water and rock, but it's really rare that we'll do anything more than 4 or 5 kilometers. I think the maximum for Expedition 391 was about 4.5 kilometers.
Yeah, that is including the water depth and the rock depth. And in this particular expedition, the last code that we got is 495 meters below sea floor. So 495 meters below sea floor core we have.
And when we're drilling into hard igneous basement, like the basalt that we've been collecting, one drill bit, like the one that we showed you out on the catwalk, can get through about 100 meters of rock. So if we want to drill deeper than that, what we have to do is pull the drill out of the hole, change the bit, and put it back into the ocean and try to find the hole that we had been drilling into.
Thank you. Thank you very much.
Hello, sir. Am I audible?
Yes, Amitav.
Yeah. So, sir, my question is that is there any research going on the lights of metamorphic petrology perspective?
I am not aware of any expedition on metamorphic rocks.
So I know that there have been expeditions that are focusing on subduction zones.
Yeah.
I think the primary objectives have been more related to volcanism, but what's really cool about these expeditions is that they take 20 to 30 scientists every time. So different scientists on the expedition will have different goals and different focuses. So if you're drilling into a subduction zone, you'll take your volcanologist, you'll take your sedimentologist, but you can also take your metamorphic petrologists.
So in your case,
yeah.
Yes, sir. Please go ahead.
Yes, Amitav. Go ahead, Amitav. Go ahead.
Okay, sir, I'm just asking that right now you're concentrating on a specific goal which is based on igneous petrology. So during this course of action, have you encountered any metamorphic rocks?
Well, so far we have not seen any high temperature metamorphic rocks as per se. If you want to call this orbitization, that is basically a fluid related alteration. It is not a metamorphism. So no, in this there is no metamorphism we have encountered. No.
Okay.
But there are places like, I believe if there are expeditions close to the continental areas, you might come across some but from your personal interest point of view, I know that each expedition requires a structural geologist to take all kinds of deformation structures, measurements in the core and all. So that is an integral part of most of the expeditions.
Okay, sir. Thank you.
Yes, I have some questions. May I ask?
Yes, sir. Yes.
Sir, my question is regarding the sedimentary part, as it's my interest. You showed there are some sedimentary core mixed up with some volcanic material as well. And from there, you are deriving that those may be some slump deposits. So my question is, from the width of the core is around 5 to 10 centimeters. That I can understand from the photos, from the video. So from this is how it can possible. And one more question is, what about the nanofossil? You didn't show the nanofossil collections that you collected during this drilling. What?
Well, about the nanofossils, there is a separate lab for working on the nanofossil foraminifera. As you know, this is the expedition with a reduced number of scientists, because as Maya explained that this was originally supposed to be only transit expedition, and later they gave permission to do some drilling and taking the core out. So it was not a full science party. In a full science party, you would have this paleontologist, as I explained in the first code, that they would be actually doing the biostratigraphy on ship. So that time, probably it was easier to show all the nanofossils and microfossils, which they would be separating out in the thin section. But I don't know whether we have any samples of that right now.
So I looked on our computers to see if we could find any images that they had taken during the previous expedition, but every expedition they erased the computer hard drives just to make space for the new expedition. So we don't have any of that, unfortunately. Every expedition, all of the samples that we collect get sent off the ship, either to scientists so they can be analyzed, or to the repositories where they're kept for legacy.
Yeah, for about your first question, you are right. I mean, whatever reconstruction we do from the core. I mean, we do not have luxury of going to the outcrop and looking at, in the entirety. If you look at the entirety, then of course it is easier to interpret, as you are correctly saying, that slump deposits, but whatever reconstruction is done based on this course.
And something that has not happened on this expedition, but sometimes happens in other expeditions when there is more time, we carry out what we call downhole logging. So after we pull the drill out of the hole, there are sensors that we put in, and so they can record the outside of the hole that we drilled into. And they use, I think they use sonar. They also record some of the physical properties, again, thermal conductivity, density, things like that. But it's, we're trying to tell stories from just this tiny amount of rock. You're right. It's all speculative, but it is based on strong geology.
Okay, thank you very much. Thank you.
I want to ask sir one question. Am I audible, sir? Yeah.
Yes, we can hear you.
Apart from studying physical properties of the hard rock collected in the course, what kind of facilities you have there on board to study the chemical properties of rocks? Like you are from the geochemistry background, so can you do some, like what kind of instruments you have access to?
Yeah, there is an ICP AES on board. There is the instrument for measuring the carbonates, total carbonate and organic carbonate. There is also a facility to measure the chemistry of interstitial waters. So they can press the sediments and take out interstitial water, and interstitial water chemistry also can be done. And there used to be a PXRF, a portable XRF, on the board, and that was a very important instrument to actually quickly see the chemical variation in trace element in the core. But it so happened, and it happened only on the first time, I guess, that in this expedition, this PXRF is not working. So we are not able to make use of the portable XRF, but a lot of work is going on ICP AES, where we are measuring some of the selected samples, because based on these physical properties and the visual inspection of the cores, and with the help of senior volcanologists like Professor Mike and others, we could divide this into at least two flows, or we are still debating whether it is single massive flow. So we are hoping that the chemical data which are being generated now, people are working them. I mean, we are all trying to get those data as soon as possible. So they would help us to actually see whether there is any distinction, chemical change. Because one thing which is very intriguing in this particular core is that there is at least 60-70 meters continuous massive basalt. And physically, it is very difficult to be in that kind of massive basalt in a single flow. But whatever expected flow boundaries, like the density of vesicles, chilled margin, fragmentation of the top, brecciation, all those things are not there. So this is something very interesting, that you do not have a very clear-cut physical markers to divide them into different flow units, even though there are some isolated signatures, like at one place we saw unusually empty vesicles lined with some kind of residual magmatic fluid. So there could be a magma injection in that, or that could be a new flow. That is not very clear yet. So these chemical data which are being generated, particularly using the ICP AES, we are hoping that that would be able to tell us something more about those things. Yeah.
Thank you, sir.
So may I ask a question?
Yes, Ushashi.
In the beginning, you told that the ridge shape is in a shape of a trident rather than a straight line normally as it is. Could it be due to the African rift? The African rift is very complex and it is still forming. So could that rift, given there we have two branches going out. So could that have any impact in the shape of the ridge? Because the hotspot will stay constant. It's only the movement of the plate that's being affected. So could the African ridge have an impact on the shape of this particular ridge?
Yeah, I mean, you are very right, Shashi. There is a strong evidence of the opening of Atlantic Ocean and the hotspot, particularly on the older part. What Maya showed you in the map, the northern part of the Valvis Ridge, and where she showed you a zigzag is there, a plateau is there. So there is one hypothesis that that is the part where the ridge magmatism and plume magmatism would have interacted. So there are some geochemical signatures which suggest that there could be some interaction of plume and the morp signatures, but this trident is further south of that, further south west of that. And interesting thing is that as you go down these three lines of the hotspot, you start getting different isotopic signatures. And that happens after a certain time. I mean, after 60 million years or so. This Atlantic Ocean, you know, started opening around 135 million years or so. So that is the northern portion of the Valvis Ridge, which actually goes to the Parana Bissau. So you have one in South America, one on the South African side. So that is where it starts. And then as you go up to 70, 60 million years, then the trident starts, three separate ridges. And they have different isotopic signatures. So that is the one major question which actually, you know, kind of justified this expedition, that why this distinction comes there. So there are several working hypotheses people are trying to test. One is, as you said, there is a microplate probably was there, and that interacted, and that microplate probably have changed the hotspot tracks. Another hypothesis is that the plumogenic zone, the magma where it comes, that has changed with time. So you started training some peripheral source magma rather than the main plume source magma. So these are the questions people are addressing, and I mean there are very accomplished geochemists on this expedition who are trying to look at the osmium isotopes, helium isotopes, besides the strontium, neodymium, lead isotopes. So all this finer isotopic work later, which will be done offshore after this expedition, and it may probably take a couple of years to come up with those answers. So what you said is right. That is one part of the hypothesis. Yes.
Hi, sir. Can you hear me?
Yes. Yes.
Sir, you showed us the codes that had a color variation, like from that dark color to the light colored one, that orange to green color. Like, what could be the reason for that? Can you just tell us again?
It appears at this stage that it is all color variation is only because of alteration. So there is not basic change in the primary mineralogy. Whatever color change we see is because of the secondary alteration. And what we understand at this point is that from the top of the core, the alteration is started with the oxidizing fluid, and as we go down, it is more reducing in nature. So you see brownish red color grading into the greenish color, that is in the pyroclastic and in the massive flow. In sediments, there are some color variation, which when Professor Mike explained, you could have seen those core light gray and dark brown color. There is one possibility that color control in sediments could be because of the enrichment of carbonaceous versus clay-rich sediments. So there was one time where clay-rich sediments were more depositing, and then there was a time when more calcareous sediments were being deposited. So that could be climate related. Yes.
So if you allow me, can I just share one photo of my field that had an exact similar pattern? Can I share it?
Okay.
Do you have a picture of it that you want to share the screen?
Yeah.
Will it let you? Let me know if I need to change the permissions.
You try sharing it.
Can I take a picture and show it here?
Sure.
Okay, in the meantime,
Meanwhile,
anyone
others,
else like to ask?
if others have any query, please use the time. Rajneesh, you said the largest depth you drilled during this expedition is 490 meters or so, right?
Yeah, below seafloor, yes.
So that was in the hotspot track, right?
Yes, that is in the hotspot, yes. You're not audible.
Oh, you muted yourself.
Sir, you got muted.
So two types of volcanic rock should be there, isn't it, Rajneesh? One is the one which came through this hotspot volcano. The other one, the previously formed oceanic crust, isn't it?
Actually, the drill was on the one they call it Geo. That is a sea mount. So that is complete hotspot volcano.
Okay, you did not reach beneath into the oceanic crust, right?
No.
Okay. So there was a oceanic crust already onto which this volcanic eruption took place, and the oceanic crust became thicker in that place, right?
Right.
So
it is
your drilling
actually
was.
This is a kind of, you can say this is an underwater volcano. So we did not go to the base of the volcano.
Okay.
So this is a seamount or a hotspot volcano, and it was drilled on the flank of that seamount. So it is within the hotspot. It did not reach to the normal ocean crust.
Okay. So all your samples are from the seamount, sir? Okay.
Yes, from the seamount. Yes.
What was the depth of water column at that place where the deepest drilling was done?
It was 2.5 kilometer, I think.
But that is the normal depth, or it's a elevated area, that one?
This is a elevated area a little bit. I do not know what is the surrounding ocean's depth. It goes up to 3.5, I guess.
Okay. I don't know.
I am not very sure, but it is quite variable.
Okay. This temperature is also measured, ambient temperature, while drilling is in progress. What was the temperature at that depth, 490 meters or so? The temperature is not measured, is it?
Temperature, I don't think was measured.
I can go run and try to find out.
Yeah, I'm not sure.
I'll see what I can find out. I'll be right back.
So Maya is going to see those log sheets if somebody has logged the temperature at the site of drilling. But I don't think that they have measured the temperature, because they have separate sensors which do the logging of the hole. That was not done during this expedition. So when they do the separate logging at the time, they measure the natural gamma radiation, they measure the temperature and other parameters. But in this expedition, I don't think that was done, because this expedition was constrained by a lot of time. I mean, we were not given enough time to do all those measurements. So major focus was to go directly to the basement, ignoring all the sediments, overlying things, and drill as much as basalt as possible.
Was it almost homogeneous, Rajneesh, the basalt, all through the depth?
Yes, sir. That was very surprising to see. It is a very homogeneous basalt of at least 60 meters, whatever. Then drilling was stopped. I mean, if we went on, then probably we would be getting the same. So we do not know what is the extent down the depth, but whatever we recovered, at least out of that 60 meters were very similar looking, homogeneous, massive flow, massive basalt.
Drilling was stopped there because of physical constraint or other reason? So that
because
was the
of
maximum.
time.
Okay.
Because of time.
How much time it took to drill through 490 meters? How much time it took?
It took, I think we were there for 3 days, 3.7 days or 3.7 days, right? There on one side.
Oh.
3-4 days it took, yeah. And continuously, I mean, this drill was, of course, it is a continuous process. So around 3-4 days, continuously it was being drilled, and we were getting core after core. So what I remember is that as long as it did not start coring the basalt, we were getting 10 meter of core section every 2 hours. And once it starts drilling the massive part of the basalt, then the drilling speed reduced. Then we were getting the 10 meter core section every 4 to 5 hours. So that was the kind of drilling speed we had. So in basalt, drilling speed was 10 meter in 5 hours, you can say. So you can say 2 meter per hour was the drilling speed for basalt. And for sediment, because some part of or top was sediment, so they were about 2 hours for 10 meters. That was the drilling speed, yeah.
It's fairly
And
quite
so
fast.
we, on this, it is quite fast. For this expedition, we did not record any temperature of the seafloor or below the seafloor. That would be, we would have to send the downhole logging tools, but we didn't have time for that. Great. Were you able to find that picture that you wanted to share?
Yes, sir.
Okay.
Is
So let's make it big.
can you see it?
Oh wow, that is quite some color variation.
Yeah, actually from here I can see it is greenish, and it slowly goes to darker. Like I got it in the field. So could it be because of this oxidization and reduction that you are telling about?
It is difficult, Kamlesh, to say from this photograph. We have to find out what rocks you are talking about, what field area, what rocks basically.
Actually, after that, there was a Archean carbonates. After that fraction, we could get the Archean carbonate fraction from there.
Oh, what are these rocks? Are these sediments, metamorphic rocks, basalts? What are these?
Mostly I think they are sediments and phyllites mixed.
Yeah, so that, I mean, I cannot say from the picture, but one has to see whether there are any change in the primary mineralogy, or if there are sediments, then are there any change in minerals? First thing you have to find out. If you find that more or less minerals are not very different, then it has to be some impurities in some grains which could be giving some coloration, and it could be related to alteration. There is one possibility, but it has to be investigated. It cannot be, it cannot.
No, I wanted to know. I wanted to know the core samples that you collected, which had that color variation. Were that like those were sediments alone, or they had any rock type?
Yeah, that is what I'm telling. The color variation in basalts was only because of alteration. Color variation in sediment was because of different provenance, which resulted in different types of sediments. So in sediments, the clay-rich part were more brownish, the calcareous sediments were more whitish. So there was a different types of sediments which were deposited. So that gave the color variation. In case of massive basalt, it was all the same flow, but because of different alteration, the color variation was there.
Thank you, sir.
Sir, am I audible?
Yes.
Sir, in one of the basalt cores, you showed that there were two set of veins, or I guess there was one white color and some greenish color. So was that in the same place, or like there are two different veins?
What I showed you is one vein which we call a composite vein, because it was filled by two different minerals. It was, in fact, you can see when you see it more closely, then you can see that vein wall is lined by one mineral and vein center is filled by the other mineral. So these are called composite veins with the two sets of minerals. And there are also the cases where there are two different types of veins filled by two different type of minerals. So we have to work out the stages of alteration. The different time of alteration has given rise to different deposits in the vein.
Yes, similar veins we found in the earlier samples also, but we had already. Yes. Like in the center, it was whitish, and in the near the walls, it was greenish.
Yes. Yeah, we are finding the similar veins in earlier samples also. Yes.
Yes. Thank you.
What about the MSc students? Are they there? Yes, Bhuvan.
Sir, my doubt is regarding the olivines. You were telling that even olivines were present in these basalts. So I hope you had a look at the thin sections. Were they serpentinized completely, partly, or are any fresh olivines preserved?
There are some sections where fresh olivines are preserved, and they are very small, but they are fresh in some sections. And there are some places where olivines are not serpentinized, but they are eating site. I mean, they have been altered to eating site. Serpentine is there, but not very common. It is only in one particular part that we have, and that also there was a vein material which we when separately did the XRD. So let me tell you here, XRD is also available. So we did a lot of XRD analysis also. So in one vein material, we get the signature of serpentine, but within the rock, we did not see any serpentinization of olivine, though we see lot of chloritization of pyroxenes and lot of sericitization of plagioclase. So that is the dominant alteration. But olivine are either fresh or they have been altered to eating site.
Sir, and are any orthopyroxenes present? Or it's only clinopyroxene?
Mostly clinopyroxene.
Okay.
Mostly augite.
Okay. Thank you, sir.
Hello, sir. Can you hear me?
Dr. Lassi. Yes.
Sir, I understand that you are planning to drill 2 sites. So both are done, or it is?
Yeah, both are done. Both are
Okay.
done. The first site did not yield the basaltic flows. They were mostly pyroclastics, lapilli stones, volcanic breccia. That is what was done on the first site. So it was decided by our chief scientist and all of us together, whether we continue drilling that. Because one thing we forgot to mention here is that before we choose this drill site, lot of preparation work goes into that. So a lot of seismic surveys are done before a drill site is chosen. So based on those seismic surveys, these drill sites are chosen. So in those seismic profiles, the characteristic of basement were not very typical of a basaltic lava flow. So it was decided that because we are getting many sections of lapilli stone and volcanic breccia, so it was decided that we will not continue that first site to a very long depth. So few sections were collected, and then we moved to the next site so that we can spend more time on the second site. So now we have completed both the sites. Yes.
Okay. So along with this coring, whether you are collecting other kind of biological samples and water samples and any other kind of information you are gathering along with this?
No, I think only these hard rocks were aimed to be collected. With that, we got some sediments, of course, but other than the sediments and the hard rocks, no other samples were taken.
There was a scientist on Expedition 391 who was collecting seawater, but he was doing that to study isotopes. I forget which isotopes, but not for biology. There are some expeditions that focus on microbiology, but not ours.
Thank you. Thank you.
Any other question from students, MSc students?
Yes, sir.
Please carry.
Sir, my question is there any reason for choosing seamounts for drilling?
Is there any reason to choosing the seamount for drilling?
Seamounts for drilling. Yes, sir.
Yeah, that was the primary objective of the expedition, to understand the origin and evolution of this hotspot magmatism, which are manifested in forms of seamounts on the seafloor. So that was the reason that those seamounts are chosen. That is correct, I think.
Yeah. It also, one additional benefit of drilling into seamounts is that they are much more shallow than the ocean floor, which means it's a lot faster to get to them and to collect samples from them.
Thank you. Sir, I'm Sandhya. Sir, is it audible to you?
Yes.
Sir, my doubt is what is the age of the study area? By thickness of the sedimentation, can we find the age of that area? Or you said foraminifera also there. So what is the age of that study area?
Yeah, well, some geochronology was done on the basalt earlier, but in this expedition, we have geochronology team also working on dating those basalts on more finer scale. So what we know is that this area was 60 million year old, the basalt, 60 to 70 million year old basalts. And the sediments, of course, have to be younger than that, but exactly what sediments were recovered, that we cannot determine right now unless we do the biostratigraphy for them. So of course, biostratigraphers would be able to tell you more precisely what is the age of those sediments. So that on board right now, we do not know.
Thanks.
Sir, I have a question not related to geology at all. It's a very general question.
Okay.
Sir, how is the food on board JOIDES Resolution?
How is the
food? How is the food? Is it tasty?
I can tell you that there are so many varieties of food here that everybody would find some food of their liking, definitely. I mean, there are so many varieties, and initially I was a bit worried that whether I would get vegetarian options or not. Then I realized that Maya also is preferably, I mean, vegetarian. Yes. So there are a lot of varieties of vegetarian food, all kinds of food, and fruits. So it is very good.
They also have a constant selection of sweets. So there are cakes, custards, puddings, cookies, all the time. There's a lot of food that they give us, and it's all good.
In fact, I don't know about others, but I am getting into problem of overeating.
Are there any more questions from students? If there are no more questions, so on behalf of students and faculty of Pondicherry University, we would like to express our sincere gratitude and profuse thanks to you, Ms. Maya, Rajneesh, and your other team members for reaching to us, for educating us. Though we are sitting so far from you, you made us feel as if we are there on board with you. So nice of you. I know your time is very precious. You have spent more than an hour with us, for us. Thank you so much. Thank you so much.
Thank you all so much as well. Thank you.
Thank you. It was a good opportunity for me to see all of you and say hi. Otherwise, I could not do that.
Yes.
Thank you.
Okay. Okay. Have a safe journey. Okay.
Thank you.
Thank you.
Goodbye.
Thank you, sir. Goodbye.
Thank you, sir.
Thank you, sir.